time, we all wish we had more of it. If only there were a way to break free from the chains of time and travel wherever we wanted through its vast expanse, to journey into the distant past or peer hundreds of years into the future. The greatest minds in the world have attempted to make this dream a reality for audiences throughout history, but success has remained elusive. Yet now, new science is revealing strange pathways, and perhaps we can finally answer the question, is time travel possible? And if so, how can we achieve it? Asterisk, the mysteries of the universe lie hidden across space, time, and life itself, waiting to be discovered through the cosmic wormholes that connect different regions of reality. In a profound sense, every man, woman, and child on this earth is already a time traveler. Whether we like it or not, we are all moving forward through time, making the journey from birth to death with no way to return and no method to glimpse what lies ahead in the future. Or is there? Imagine if we could travel backward through time, witnessing the events of the past with our own eyes, or perhaps venture far into the future to see our own destiny unfold before us. Think about how much we could learn if we could watch history unfold right before our eyes, or consider what we might change in our own lives if given the opportunity. Asterisk, for many people, life's greatest sorrow is losing a loved one. When I was a child, the time I spent with my grandmother was precious beyond measure. She was the one who helped shape me into the person I am today. I often find myself wishing I could see my grandmother again, or travel back through time to show her who I am now and how I've grown into the person she helped me become. This seems like an impossible dream, a fantasy beyond the reach of reality. But is it really? Can science find a way to bridge the gap between the present and the past? Is time travel truly possible? Asterisk, to find the answer to this question, we must first understand the nature of time itself, and that proves to be far more difficult than it might initially appear. Steve Jeffords is a nuclear scientist and an excellent timekeeper. He believes that we all have an intuitive sense that we understand time. It passes by us quickly, moving forward relentlessly. We grow older with each passing moment. Events that happened in the past are not happening now in the present. But Steve doesn't think any of us, whether we're physicists researching the nature of time or just ordinary people living our daily lives, truly understand what time actually is at its most fundamental level. Asterisk, Steve works at the National Institute of Standards and Technology located in Boulder, Colorado. This facility is one of only 6 laboratories in the entire world that calculates coordinated universal time, which serves as the official world time standard used across the globe. This table, filled with an array of sophisticated lasers and optical equipment, houses the NIST F1 cesium fountain atomic clock. This remarkable instrument measures the nuclear vibrations of cesium atoms with extraordinary precision. The clock ticks 9 billion times per second, which equals 10 million times the duration of 1 nanosecond. This clock can measure frequency, or time intervals, with an accuracy reaching approximately 16 decimal digits of precision. Asterisk, but why is this level of precision so critically important? There are many reasons why measuring time or frequency with such extraordinary accuracy matters. And truly, there are numerous applications. Some of these reasons are purely scientific in nature, advancing our understanding of fundamental physics, but many are actually extremely practical and affect our daily lives in ways most people never consider. Take the global positioning system, for example. GPS is essentially a time-controlled system at its core. We place atomic clocks on satellites orbiting the Earth and ensure that all of these clocks are synchronized with each other with incredible precision. When you stand somewhere on Earth with your GPS receiver in hand, it receives time signals from these satellites. The device simply measures the arrival time of these signals with extraordinary accuracy. If the signal from one satellite arrives 5 nanoseconds before the signal from another satellite, the system calculates that you are 5 feet closer to the first satellite than to the second one. By using signals from 4 different satellites simultaneously, the system can calculate your exact X and Y position coordinates, as well as your height above sea level. In this way, you have determined your precise location based entirely on time measurements. The fact that this system works with such absolute accuracy is truly astounding when you think about it, but it depends entirely on the accuracy of time calculation at the nanosecond level. If you didn't have nanosecond level accuracy in your measurements, you wouldn't be able to determine which satellite you're closer to, and the entire system would fail to function properly. Asterisk, this type of precise time-controlled system makes our high-tech, computer-based lifestyle possible in countless ways. As time control systems become increasingly accurate and sophisticated, we discover that time doesn't flow in the uniform way we always assumed it did. Time is not universal in the way we intuitively believe. The strange truth is that time is personal and relative. What time it is now depends on where you are located and what the ground beneath your feet is doing at any given moment. Asterisk, whenever you place a clock within a gravitational field, something remarkable happens. As you move closer to stronger zones of the gravitational field, the clock's speed slows down relative to clocks in weaker gravitational fields. What ultimately becomes clear is that Earth is not a rigid, unchanging sphere. Earth is somewhat like a softball made of gelatin, constantly flexing and moving. Every day, as high and low tides come and go across the planet, the Earth becomes distorted like a ball being squeezed, and the ground beneath your feet moves up or down by approximately 1 foot. This depends entirely on where you're standing on Earth at any particular moment. If I lift this clock up by 1 foot, moving it farther from Earth's center, the gravitational force acting on it becomes slightly weaker. As a result, the tick-tock speed of the clock becomes slightly faster. So now, if you have a clock that displays time accurately to 17 decimal digits of precision, you can actually observe that every day the clock's speed sometimes increases and sometimes decreases. This happens because Earth is squishing and expanding by about 1 foot throughout the day due to tidal forces. Asterisk, human beings cannot perceive these microscopic time differences with our limited senses. However, our fastest and most accurate clocks can divide 1 second into 1 quadrillion separate parts. At that extraordinary level of precision, we can clearly observe that time varies according to spatial position and gravitational strength. Time and space are deeply interconnected in ways that challenge our everyday intuition. Very rapidly, we are approaching the point where we must think about space and time together as a unified entity, rather than as separate, independent concepts of space and time. This is a fascinating theory that has profound implications for how we understand reality. Asterisk, gravity slows down time, and this phenomenon is actually one form of time travel that we can observe and measure today. When you move away from a gravitational field, such as when you leave Earth's surface and travel into space, time passes at a different rate for you compared to your friends who remain on Earth's surface. The time difference becomes most dramatic when you travel at extremely high speeds, approaching the speed of light. This means that time travelers are actually living among us right now, and their time machines are all around us. Asterisk, these are their time machines, spacecraft and space stations orbiting high above our planet. Cosmonaut Sergei Krikalev is one of the world's greatest time travelers by this measure. Krikalev spent 803 days traveling at speeds of 17,000 miles per hour in orbit around Earth. He traveled rapidly outside Earth's gravitational field, so for him, time moved more slowly compared to those of us on Earth's surface, because time passed at different rates for him and for us. He has effectively traveled into the future. He is now 1/48th of a second ahead in time compared to where he would have been if he had remained on Earth. 1/48th of a second doesn't sound like very much when you first hear it, but if we could give him much more power and increase his speed closer to the speed of light, approximately 670 million miles per hour, then things would start to become truly strange and counterintuitive. If he could travel at near light speed for 1 year as measured on his clock, when he returned to Earth he would discover that while he had aged only 12 months, a full 10 years would have passed on Earth. His friends and family would be 10 years older, while he remained relatively young. Here is another type of time machine, and this one can accelerate things to speeds far faster than any rocket ship could ever achieve. This is Europe's Large Hadron Collider, the LHC, the world's most sophisticated and powerful particle accelerator ever constructed. Professor Steve Nan works at MIT and is a professor of physics. With the help of the LHC, Nan and thousands of other scientists from around the world transform tiny fragments of atoms into time travelers on a microscopic scale. They take protons, accelerate them to speeds approaching the speed of light, and then smash them together in spectacular high-energy collisions. After the explosion, all the subatomic particles that emerge exist for only billions of a second under normal circumstances, but in the LHC, traveling at near-light speeds, that 1/1,000,000th of a second stretches out relative to our time frame. From our perspective, these particles exist for much longer than they should according to their normal decay rates. Asterisk, the LHC located in Switzerland functions like a kind of time machine. And the reason for this is a strange phenomenon in physics. Velocity is not what you think it is at an intuitive level. At normal speeds, velocity behaves in the way we expect from everyday experience. But at very high speeds approaching the speed of light, velocity has a highest limit that cannot be exceeded. The protons spinning around in the LHC's ring are traveling at speeds incredibly close to the speed of light, but they cannot go faster than light. Instead of continuing to accelerate beyond the speed of light, their internal clocks slow down dramatically. Their ticks become longer compared to our ticks in the external reference frame. So in a way, the protons spinning around in the ring have clocks that are running slower compared to our clocks. Therefore, they are like time travelers relative to our frame of reference. The time-traveling protons in Switzerland demonstrate to us that we too could travel far into the future. If we had the right technology, in the coming decades, spacecraft traveling at speeds close to the speed of light could embark on what seems to the crew like a 10-year mission to the stars. For the people aboard the spacecraft, the journey would indeed be only 10 years as measured by their clocks and their biological aging. But when they returned to Earth, they would discover that 1,000 years had passed on our planet. The astronauts would arrive to find a completely transformed world, with technology, society, and possibly even the human species itself evolved in ways they could never have predicted. Time travel into the future is definitely possible with the right technology. But is this only a one-way journey forward through time? Can we fulfill our dream of traveling backward, as well as forward through time, with the right technology? Time-traveling spaceships can definitely take us into the future. But can we break the bonds of time and travel into our own past? Perhaps it's not as difficult as it seems, because the past is actually all around us in a very real sense. Think about it for a moment. The speed of light is 186,000 miles per second. While that's incredibly fast, by human standards, when light travels from here to there, it takes time to make the journey. This means that wherever you look, you are seeing into the past, not the present. Light takes even a billionth of a second to travel just 1 foot. So you see the person sitting next to you as they existed 1 billionth of a second ago, not as they exist right now in this precise instant. The light from the sun takes 8 minutes to reach Earth, so when we look at the sun, we're seeing it as it was 8 minutes in the past, not as it exists right now. And the deeper we look into space, the further back in time we are actually peering. Satellites have captured photographs of the edges of the observable universe, showing us objects that are approximately 13.7 billion light-years away. This means we are seeing them as they existed 13.7 billion years ago. Not long after the Big Bang itself, we are always looking into the past. But this is a passive form of observation, not true time travel in the sense we dream about. The matter becomes much more complex when we consider actually traveling to and interacting with the past rather than merely observing it from a distance. According to Einstein's theories, time is exactly like space in certain fundamental ways. Just as every part of space exists here and now simultaneously, every moment of time should also exist simultaneously in what physicists call the block universe model. Sean Carroll is a professor of physics at the California Institute of Technology and one of the leading thinkers on the nature of time. Physicists generally tend to be eternalists in their philosophy. They believe that the entire universe and the entire fourth dimension of time in which we exist are completely real in every sense. We exist at different moments throughout this space-time continuum, and we experience different things at different moments in time. But it's not the case that future time is becoming real as time passes. Perhaps the truth is that the future is just as much in existence as the past. We are traveling through time and discovering what happens in the future moment by moment. But the future is not becoming real in any fundamental sense, just as the past is not becoming less real as time passes. So theoretically, the past and future are just as much in existence as the present moment. All of time is laid out before us in the four-dimensional structure of space-time. But can we jump from the present into the past and actually interact with it? In the early 20th century, a patent clerk named Albert Einstein showed us that this possibility might exist within the laws of physics. While going to work one day, the approximately 20-year-old Einstein looked toward a clock tower, and suddenly everything fell into place in his mind. Einstein understood in that moment that time depends on where you are and how fast you are moving through space. Time is a fourth dimension that is deeply connected with the three dimensions of space. length, width, and depth. A few years later, Einstein created a mathematical map of the universe to understand the effect of gravity on space and time. He proved that the fabric of space and time is curved by the presence of mass and energy. Asterisk, if the universe is curved, then there might be ways to create bridges within it or to create loops within its structure. Loops that could make time travel possible. In 1949, the mathematical genius Kurt Gödel reached the same conclusion through his work. Gödel was a close friend of Einstein, and he decided to examine whether his great friend's equations would permit time travel. Under any circumstances, he discovered that they actually do allow for time travel under certain conditions. If the universe rotates on an axis, and you could somehow remain perfectly still relative to that rotation, it would become possible to travel to any time and place in the universe by following the appropriate path through the rotating space-time. This was an exciting discovery that generated tremendous interest in the physics community. Asterisk, but we now know that the universe does not rotate as a whole in the way Gödel's solution required. Without that cosmic rotation, time travel of this type cannot occur. Gödel's solution was physically unrealistic for our actual universe, but his revolutionary thinking inspired a new generation of explorers to push the boundaries of what might be possible. Professor Frank Tapler was one of those rebel physicists who followed in Gödel's footsteps. He was greatly inspired by Gödel's paper, which he read during his undergraduate studies at MIT. He wondered whether he could build upon Einstein's suggestions in a way that would be physically realizable. Could this actually be done in practice? You can't spin all of space itself, after all. The universe either already rotates or it doesn't. But perhaps you could do something similar on a smaller scale. Using a massive rotating object, asterisk, to properly prove relativity, an easy model to work with was a rotating cylinder. That's why Tapler showed that a rotating cylinder creates loops in time that give us the capacity to travel backward through time. Tapler's massive cylinder would hang in space and rotate at nearly the speed of light. As it rotates, space transforms into time and time transforms into space around the cylinder, because both are curved around it. Therefore, if you move around the cylinder in the right way, you can move backward through time. The direction of time normally points this way, forward into the future, but around a very rapidly rotating object. You can only travel in a spiral path. By following this spiral path around the rotating cylinder, you can move backward through time. Asterisk, Tapler wanted to publish a research paper with the title Constructing a Time Machine, but the publishers felt that this title was a bit too radical for a serious physics journal. They wanted something that sounded more scientific and academically respectable. Therefore, he later changed the title to Rotating Cylinders and the Possibility of Global Causality Violation. This was such a complex title that someone could only understand what it meant if they read the entire research paper carefully. But Tapler later found some fundamental problems with his idea. He realized that although rotating cylinders might be an easy solution to Einstein's equations mathematically, they were not very realistic physically. This is because you would need an infinitely long cylinder, and creating an infinite cylinder is as complex as creating an entirely new universe, which is clearly impossible. So Tapler thought about whether such a structure could be built on a much smaller scale, using finite materials. Unfortunately, he found that this would not be possible. If you try to spin any object fast enough to create time machine properties, you would create a hole in space and time before the time machine properties could fully develop. You would create a singularity, a point where the equations break down and physics as we know it ceases to function. So unfortunately, Tapler had to abandon his dream of building a practical time machine using this method. Asterisk, Tapler's spinning cylinder cannot work in practice, but there are some massive objects in the universe that are already spinning at speeds close to the speed of light. Black holes. The immense gravitational force of a black hole pushes the laws of physics to their absolute extreme limits. Black holes are small, but incredibly powerful objects scattered throughout the universe. The infinite gravity of a black hole bends space and time far more than any other object we know of. Can we harness the power of black holes for our own purposes? Can we use them for time travel? Asterisk, a black hole is not a time machine in the sense we usually imagine. If you fall into one, you will be crushed and destroyed by tidal forces. We still don't fully understand black holes despite decades of research, but no evidence has emerged to suggest that they can take us backward in time. A black hole is, in a sense, a one-way street. You can enter it, but you can never come back out once you cross the event horizon. So black holes are not useful for the kind of time travel we dream about. Asterisk, but there is another cosmic anomaly that science fiction has made famous, and perhaps this could work for time travel purposes. Wormholes. Wormholes are magical doorways that connect to remote locations in space and time. These cosmic sky bridges could allow us to travel long distances through space and to journey through time. If you enter a wormhole, you could reach some other place or time through a shortcut that bypasses the normal structure of space-time. We have no evidence that wormholes actually exist in nature, but there is solid science behind the concept that makes them theoretically possible. Asterisk, no one knows more about wormholes than the famous physicist Kip Thorne. If you have an apple and a worm bores a hole through it to reach the other side, you can think of the surface of the apple as representing our universe. The worm reached the other side by traveling through a higher dimension, taking a shortcut through the interior of the apple rather than crawling around its surface. If wormholes truly exist in nature, they might be even smaller than atoms in their natural state. If we are to pass through them, we would need to expand them and keep them open, which would require enormous amounts of energy. Asterisk, opening a wormhole would require not just any energy, but something called negative energy. Negative energy is anti-gravitational in its properties. It repels the fabric of space-time and can prevent gravity from causing the wormhole to collapse. One problem with this concept is that many people don't believe negative energy actually exists in our universe. An energy that could be anti-gravitational sounds very unrealistic and contrary to our everyday experience. But actually, in modern physics, we have examples of negative energy that are created in laboratories every single day. These are very small quantities of negative energy, often transient and short-lived, but it is nevertheless genuine negative energy. Therefore, Thorne was not prepared to dismiss this possibility entirely. The important question is whether an advanced civilization could store sufficient negative energy and maintain it within a wormhole long enough for a human being to travel through it safely. We don't know the answer to this question yet. Asterisk, meanwhile, another renegade physicist discovered a different way to use the time warping effects of celestial phenomena. Richard Gott has been studying the problem of time travel for decades. Gott's unique time machine uses the heavy gravity around cosmic strings to create loops in time. Cosmic strings are thin streams of energy that could stretch across the entire universe. There's a famous poem about a young girl named Bright who traveled at speeds faster than light. She disappeared one day in a strange way and returned home the previous night. But the problem is that Einstein has proven that you cannot build a machine that can travel faster than light. However, general relativity, which is based on the principle of curved space-time, suggests that if you take a shortcut through curved space, you might be able to effectively travel faster than light by taking a shorter path through space-time. Asterisk, so this is the method by which you could travel around cosmic strings and, like Miss Bright, tour events in your own past. Many physicists believe these cosmic strings might exist in our universe. They are fragments of high-density vacuum energy that were created during the Big Bang. They could be thinner than an atomic nucleus, but stretch for enormous distances across space. Some cosmic strings might be small and localized, while others might be infinitely long, stretching across the entire observable universe. But all of them would have incredible gravitational effects on the space-time around them. Wherever there is extreme gravity, there is potential to create a shortcut in space and time. Asterisk, so here is how you would build a time machine using cosmic strings. You can think of the geometry around cosmic strings as being like a flat pizza slice, but actually, because these strings have so much mass per unit length, the space-time around them looks like a pizza with a slice removed. If I cut out a part of the pizza here and remove it, then fold the pizza so it forms a cone shape, the entire pizza would look like a cone. If I'm on planet A here, I can send a light beam to planet B, but if I board a spaceship, I can travel at a speed slower than the speed of light and still reach there using this shortcut, arriving before the light beam does. This means that my departure and my arrival are more separated in space than they are in time. In other words, the distance might be for light years, but the journey might take only 3 years of time. Asterisk, so what can you do next? I can cut another slice out of the pizza, and now I have the cosmic strings creating an even more dramatic warping of space-time. Twist this like a boat. And this is the structure that appears in space-time around the cosmic strings. Now what can I do? If I travel with my spaceship around these cosmic strings, In the right pattern, I can return to planet A at 12 noon. Now, 12 noon on planet A is the same time and location from which I departed earlier. So my older self can return and shake hands with my younger self, who is just departing. In this way, my older form can return and watch myself saying goodbye as I leave. I am participating in an event in my own past. This is genuine time travel into the past becoming possible. Asterisk, but once again, there are one or two significant problems with this approach. For starters, when you bring the cosmic strings together at high speeds, they might create a black hole. You could be killed after completing your time travel, or even before completing it. The second problem is that if you only want to travel 1 year into the past, the mass of this loop would equal half of our entire galaxy. Therefore, this is a project that only super civilizations far more advanced than ours could even attempt. It is far beyond our present capabilities and will likely remain so for many centuries, or even millennia. Astrophysicists like God do not claim they can build a working time machine today with current technology. They are trying to understand whether the laws of physics permit time travel in principle, not whether we can actually do it right now with our limited resources. All the possible methods for building a time machine have several inherent problems. One of these is that nature seems to have a driving force that would cause a time machine to self-destruct at the very moment you try to activate it. This is sometimes called the chronology protection conjecture, first proposed by Stephen Hawking. Asterisk, can this problem be overcome? The answer seems to lie hidden in the laws of quantum gravity, laws that we don't yet fully understand. We know how. Gravity affects large objects like humans, our planets, and stars in space. But we don't understand how it works at the quantum level, where waves and particles blur together in strange and counterintuitive ways. But not understanding something has never stopped people from experimenting and trying to push the boundaries of knowledge. Asterisk, at this moment, another group of explorers is trying to find answers to the secrets of time travel in the place you would least expect it, at the exact center of an atom. It seems that time travel is nearly impossible in Einstein's world of space and time on large scales. But there is another world, another branch of physics, where Einstein's rational laws don't always apply. This is the world inside the atom, where the bizarre laws of quantum mechanics operate. Don't be frightened by this. It's strange, certainly, but also extremely exciting. Astro's quantum mechanics is basically the concept that what exists is far more complex and vast than what we can see with our senses or even with our best instruments. When you look at a particle, you see it in only one place at one specific moment. Quantum mechanics says that when you're not observing it, that particle can exist everywhere simultaneously, in a superposition of all possible states. Perhaps there's a higher probability that you'll observe it in one particular place, but actually it exists across a spectrum of many possibilities until the moment of observation. So when you combine the concepts of quantum mechanics with the concepts of time travel, everything becomes chaotic and difficult to predict. One of the strangest features of quantum mechanics is called non-locality. This is the condition where the particles instantly influence each other, even though they might be separated by miles or even light years of distance. It's somewhat like voodoo magic in a way. When you stick a needle in the doll, the person connected to it is also affected. But unlike voodoo, quantum non-locality is scientifically proven beyond any reasonable doubt. Asterisk, today, Swiss banks are conducting experiments to see whether non-locality can be used to create completely crack-proof security keys for computer transactions. Professor Nicholas Gizon is leading this research. Gizon is a quantum physicist and fiber optic specialist. He has conducted tests on quantum non-locality showing that photons of light, even when separated over considerable distances, remain perfectly synchronized. Quantum physics says that when you perform an action on one photon, the reaction doesn't occur only on that photon. Instead, there's a global reaction affecting both photons simultaneously. In a way, these two photons, even though they're far apart from each other, remain part of the same unified system. That's why the global system reacts together, and this is quantum non-locality. Asterisk, Gizon sends photon signals through fiber optic cables spread across Geneva. At one end, a pair of photons is activated by a laser, and the photons at the other, and react instantly. Nothing appears to travel between them, and no energy is exchanged that we can detect. Yet somehow these particles are sharing information instantaneously across space. Einstein called this spooky action at a distance. This spooky action is not something traveling through space-time. It's not something moving directly through the middle of space-time that we can observe. There's no clarification in space-time that explains how these non-local correlations happen. And this is the reason we conclude that they are somehow created from outside space-time itself. This definitely has a profound impact on our understanding of space-time, or better said, it highlights our problem of not understanding space-time. Some people believe that quantum non-locality could be used to send messages backward through time. At the University of Washington, physicist John Kramer is testing this concept, like Gizon. He's also experimenting with entangled photons connected through non-locality. The difference is that Kramer is trying to send photon signals from the present into the recent past. These specially designed lasers and measuring devices called interferometers are the core of Kramer's time machine. An interferometer called Alice sends photon signals to another interferometer called Bob. If Kramer's theory is correct and the calibration is perfectly precise, Bob will receive the signal from Alice before she sends it. Cause and effect will be reversed. So Alice will have control over whether we get particle-like behavior or wave-like behavior here, at her end. Because the photons are entangled in space, Bob, who wants to receive the signal here, can observe whether he's receiving an interference pattern at the same time. If this distance is just a few centimeters, that's not very large. But it doesn't have to be just a few centimeters. It could be a light year of distance, and it could still do the same thing and have the same effect here. That's how entanglement works. So if I put a reel of fiber optic cable 10 kilometers long here, the signal would be sent 50 microseconds after Bob receives it. This means she would be sending messages 50 microseconds backward in time, so in principle, this could be used for communication backward through time. If Kramer's device works as intended, it will only be able to send messages back 1/millionth of a second before they are sent. But if any signal can present itself in the past, even by this tiny amount, it could revolutionize our understanding of time. It would prove the principle of retrocausality, meaning that future events can influence past events. If this works, it would be remarkable and would be a huge development in physics. It would also be a tremendous achievement in the communications industry. If you can send messages backward through time, it would be a huge thing everywhere. It would change our civilization in ways that are difficult for me even to imagine. But all of this might just be a signal that this experiment will probably not be successful, because nature perhaps doesn't want to permit you to send signals backward through time. I don't actually consider retrocausality to be a very universal concept in physics. I mean, time clearly develops or grows toward the future. On the other hand, I would also say that time is definitely one of the concepts in physics that is only half understood by today's scientists. It can be completely expected that in the future, we'll have a much better and deeper understanding of time. Perhaps this understanding will be completely different from our current comprehension. So let's assume that someday we develop a deeper understanding of time. After solving the puzzle of quantum gravity, suppose we build a working time machine that can actually take us into the past. What happens then? Can we go into the past and change it? The answer is amazing, disturbing, and somewhat strange. We are trying to send signals backward through time, and if this works, one day we might be able to send humans backward through time as well. This is an exciting thought, but it opens the door to the problem of paradoxes. A paradox is a situation that contradicts itself and makes no logical sense. Imagine you send the cure for cancer from the future into the past. Would dead people suddenly be alive now? You see, time travel is full of such mysteries and logical contradictions that are difficult to resolve. The things we want to understand about time travel are, first, is it theoretically possible that the laws of physics permit time travel into the past? We don't know the answer to this yet. To know the answer, we would need to understand the laws of quantum gravity. The second question is this: if travel backward in time is possible, what does nature do about the so-called grandfather paradox? If it's possible, I could travel backward in time and kill my grandfather before my father is born. This would change history and mean I would never come into existence. What does nature do about this logical contradiction? One conservative explanation is that space-time is a four-dimensional structure that doesn't change. Therefore, if time travelers go into the past, they have always been part of the past, and they don't change it. In other words, if time travelers were present on the Titanic, they could have warned the captain about the iceberg, but he didn't pay attention to them. Just as he didn't pay attention to other iceberg warnings, because we know that the ship ultimately did hit the iceberg. We know what happened. So this is the conservative approach. Time travelers don't change the past. They can participate in the past, but they cannot alter what has already happened. Someone actually joked that the real thing that sank the Titanic was the extra weight of all the hidden time travelers who came to watch it sink. Actually, there's a straightforward reason why we're not surrounded by time-traveling tourists from the future. It's because no one has built a working time machine yet. If someday we have the technology to travel backward through time, that machine would only work from the point at which it was created, when the first loop in time was established. If you build a time machine in the year 3000 by manipulating cosmic strings, you are bending space and time to create a time loop in the year 3000. So when a time traveler travels, they always move toward the future along this loop, like this car. They go around the loop. This means they can go from the year 3000 and back to 3001. But they cannot come back here to the year 2010, because that's before the time machine was built. But there might be an exception to these laws. And once again, this is related to the strange world of quantum mechanics. Many quantum physicists believe that countless parallel universes exist, and these parallel universes are spread all around us in higher dimensions. Every time you make a decision that could go into directions, for example, you flip a coin, it could go the other direction as well, and then space splits into two different branches. If we accept the possibility of parallel universes, then much becomes possible. It's still true that factual paradoxes must be avoided. What happened has happened and will always be true. But this means that what happened in one universe only happened in that universe. It won't apply to new universes. If multiple universes exist as quantum physics suggests, then if you go into the past and kill your grandfather, you are killing someone who is similar to your grandfather. But they would only be your grandfather in a parallel universe. In a parallel universe, when you came from another universe and killed your grandfather, your father, and therefore you will never be born in that universe. But there's no problem with this because in that universe, you never existed in the first place. What you did with your time machine was simply travel between universes, not actually change your own timeline. But in the near future, the possibility of time travel seems very unlikely, whether in the present, past, or any parallel universe. The technology needed to build a time machine, even one with the slightest signal of success, is as far beyond our current capabilities as space travel would be for an amoeba. Because our technology is still very weak, there seems to be no hope. Time travel appears impossible if we define it only as a process of taking a person or information from the present and sending them backward into the past. But there is another way to experience the past, a method that until recently would have been considered absurd, but which is getting closer to reality every day. We can recreate the past. Human technology is developing rapidly. When our computers become powerful enough, they will be able to simulate extremely complex worlds, including past eras of Earth's history. These won't just be video games. These simulations of the past will be so realistic that you won't know they're not real. Not the actual past, but the closest thing to it. If you really want to go into the past, you would have to go into the very distant future. In the distant future, they will have the capability to recreate the past, and then you can see what the past was like. You could actually experience the distant past by living in the virtual reality created by the powerful computers of the future. We have seen that traveling into the distant future is possible through relativistic effects and time dilation. But this is essentially a one-way journey forward through time. Time travel into the past may be theoretically possible under certain exotic conditions, but it would require unimaginable quantities of energy and God-level technology far beyond anything we can currently conceive. Our best hope for experiencing the past may lie in computer-generated simulations created by advanced future civilizations. So it seems that we won't be able to travel backward through time to meet the people we have lost or to correct the mistakes we made when we were young. Our travel through time from birth to death remains the one experience that all living organisms share equally. Every human being must live with the truth that we achieve successes, and we make mistakes along the way. If we could go backward through time and fix those mistakes, will we actually learn anything from them? Will we be the same people today that we are now? For now, at least, we cannot turn back the clock of time, but we will keep trying. We will never stop trying to understand the mysteries of time and to push the boundaries of what is possible. *# the philosophy of time and human experience. The quest to understand and potentially manipulate time raises profound philosophical questions that go far beyond the realm of pure physics. What is time, really? Is it something that exists independently of human consciousness, or is it merely a construct of our minds trying to make sense of the changes we observe around us? Ancient philosophers grappled with these questions thousands of years before Einstein revolutionized our understanding of space-time. The Greek philosopher Heraclitus famously said that you cannot step into the same river twice, recognizing that everything is in constant flux. Time, he understood, is the river in which we are all swimming, always moving forward, never returning to where we have been. The Roman philosopher Augustine of Hippo pondered deeply about the nature of time and concluded that it exists primarily in the human mind. The past, he argued, exists only in memory. The future exists only in anticipation, and the present is merely a knife edge, an infinitesimally thin boundary between what has been and what will be. If Augustine was right, then perhaps time travel in the physical sense we imagine is fundamentally impossible, because there is no past or future to travel to, only an eternal present moment that we experience sequentially as our consciousness moves through it. Modern physics has given us tools to measure time with extraordinary precision, but it has not necessarily brought us closer to understanding what time actually is at its most fundamental level. In fact, in many ways, physics has made time more mysterious than ever before. Einstein showed us that time is not absolute and universal as Newton believed. Instead, it is relative and personal, depending on motion and gravity. Quantum mechanics has revealed even stranger aspects of time, suggesting that at the smallest scales, the clear arrow of time from past to future may not exist in the way we experience it in our everyday lives. Some physicists have even questioned whether time truly exists as a fundamental feature of reality. In certain formulations of quantum gravity, time emerges as an approximate concept that only makes sense at the macroscopic scales we inhabit, but which breaks down completely at the Planck scale, the smallest possible scale of space and time, where quantum effects dominate completely. If these theories are correct, then asking whether time travel is possible may be like asking whether you can travel to a place that doesn't actually exist except as a convenient fiction. We used to organize our experiences, *# the arrow of time, and entropy *. One of the deepest mysteries about time is why it has a direction at all. The fundamental laws of physics, from Newton's mechanics to Einstein's relativity to the standard model of particle physics, are all time symmetric. This means that these equations work equally well whether time runs forward or backward. If you filmed fundamental particles interacting and then played the film backward, you would see processes that are just as physically valid as the forward-running version. Yet our everyday experience tells us that time has a definite arrow pointing from past to future. Eggs break, but never spontaneously reassemble. Coffee and milk mix together, but never unmix. We age, but never grow younger. Heat flows from hot objects to cold objects, never the reverse. The answer to this mystery lies in thermodynamics and the concept of entropy. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. This is not because the fundamental laws of physics prefer disorder over order, but rather because there are vastly more disordered states than ordered ones. If you drop a glass, there's only one configuration where all the pieces fit together perfectly to form an intact glass. But there are countless ways for the broken pieces to scatter across the floor. Randomness naturally leads systems from rare, ordered states to common, disordered ones. This increase in entropy gives time its arrow. The past is the direction of lower entropy, and the future is the direction of higher entropy. This seems straightforward enough, but it leads to a profound puzzle. Why was the entropy of the universe so incredibly low? At the Big Bang, the early universe was in an extraordinarily ordered state, far from thermal equilibrium. If the universe had started in a maximum entropy state, nothing interesting would have ever happened. There would be no stars, no planets, no life, and no conscious beings wondering about the nature of time. The fact that we exist to ask these questions is intimately connected to the fact that the early universe had very low entropy, creating an enormous entropy gradient that drives all the interesting processes in the cosmos, including life itself, asterisk some. Cosmologists speculate that our universe may be just one bubble in a vast multiverse, and that the particular bubble we inhabit happened to start with low entropy purely by chance. Others propose more elaborate scenarios involving cycles of universal expansion and contraction, or universes spawning other universes with different initial conditions. These ideas remain highly speculative, but they demonstrate how the arrow of time is connected to the deepest questions about why our universe exists in the form it does. Asterisk ## practical applications of time dilation asterisk while traveling backward through time remains in the realm of science fiction and speculative theoretical physics. Traveling into the future is already a demonstrated reality, even if only by tiny amounts. The principles of time dilation have practical applications today and will become increasingly important as our technology advances. GPS satellites must account for relativistic time dilation effects, both from their orbital velocity and from the weaker gravitational field they experience compared to the Earth's surface. If these corrections were not made, GPS positioning errors would accumulate at a rate of about 10 kilometers per day, rendering the system completely useless for navigation. As humanity begins to venture deeper into space, time dilation effects will become more noticeable and will need to be carefully managed. A mission to Mars and back at conventional rocket speeds would result in only a few seconds of time difference between the astronauts and people on Earth. But a mission to a nearby star system at a significant fraction of the speed of light could result in decades or even centuries passing on Earth while only years pass for the crew. This creates not just technical challenges, but also profound social and psychological ones. Astronauts on such missions would be saying goodbye to everyone they know, effectively traveling into Earth's future. When they return, their friends and family might be aged or dead, and the world would have changed in ways they could never predict. Astronauts some have proposed using these time dilation effects deliberately for long-term space exploration. If we could accelerate a spacecraft to 99% of the speed of light, a journey to a star 100 light-years away would take only 14 years. From the crew's perspective, though more than a century would pass on Earth, this could make interstellar exploration feasible within a human lifetime, at least for the travelers. However, the energy requirements for accelerating even a small spacecraft to such relativistic speeds are truly staggering, far beyond anything our current technology can achieve. The challenges are not just technological, but also concern fundamental physics. At such high speeds, even tiny particles of interstellar dust would impact the spacecraft with the energy of nuclear weapons, requiring unprecedented shielding technology. Asterisk ## the search for quantum gravity asterisk the quest to understand time travel ultimately leads us to one of the greatest unsolved problems in physics, reconciling quantum mechanics with general relativity to create a theory of quantum gravity. Quantum mechanics describes the behavior of matter and energy at the smallest scales with extraordinary accuracy. General relativity describes gravity and the large-scale structure of space-time with equally impressive precision. Yet these two theories are fundamentally incompatible with each other in their current forms. Asterisk quantum mechanics requires a fixed background of space and time in which particles and fields evolve. General relativity tells us that space and time themselves are dynamic, curved by the presence of matter and energy. When we try to apply quantum mechanics to gravity itself, treating space-time as a quantum field, we get mathematical nonsense infinities that cannot be removed by the standard techniques that work for other quantum field theories. This suggests that something fundamental is missing from our understanding. Asterisk many physicists believe that a correct theory of quantum gravity will reveal new insights about the nature of time itself. String theory, one of the leading candidates for quantum gravity, suggests that the fundamental constituents of reality are not point-like particles, but tiny vibrating strings existing in 10 or 11 dimensions. Most of these extra dimensions are curled up so tightly that we cannot perceive them directly, but they may play a crucial role in how gravity operates at quantum scales. Asterisk loop quantum gravity. Another approach to the problem suggests that space-time itself is not continuous, but is made up of discrete quantum units at the Planck scale, approximately 10 to the minus 35 meters. At this scale, smooth space-time breaks down into a foam-like structure of quantum geometry. Time itself may be emergent from more fundamental quantum processes that don't involve time at all. If this is correct, then asking whether time travel is possible may be like asking whether you can break a fundamental law. That doesn't apply at the level where time truly exists. Asterisk, other researchers are exploring even more exotic possibilities. Some propose that time itself may have multiple dimensions, just as space does. Others suggest that the flow of time may be related to the growth of quantum entanglement. Throughout the universe, these ideas remain highly speculative, but they demonstrate that our understanding of time is still very much a work in progress. Until we have a complete theory of quantum gravity, we cannot definitively say whether backward time travel is possible or forever forbidden by the laws of nature. Asterisk ## causality and the structure of reality. Asterisk, one of the most troubling aspects of backward time travel is that it seems to violate causality, the principle that causes must precede their effects. Our entire understanding of how the universe works is built on causal relationships. We observe that one event leads to another in a logical sequence. Science itself is fundamentally about discovering these causal relationships and using them to predict future outcomes based on present conditions. If time travel allows effects to precede their causes, the entire logical structure on which science is built seems to crumble. Asterisk, the grandfather paradox is the most famous example of this problem, but there are many others. Imagine you travel backward in time and prevent the invention of the time machine that allowed you to travel backward. This creates a logical loop with no consistent solution. You can only prevent the invention if you can travel back, but you can only travel back if the invention occurs. Some resolutions to this paradox have been proposed. The consistency principle suggests that any time traveler's actions in the past are already part of history and cannot change what happened. They can only fulfill what has always happened. Asterisk, this creates what physicist Igor Novikov called a self-consistency principle for time travel. The laws of physics would somehow conspire to prevent any paradoxical situations from occurring. If you tried to kill your grandfather, quantum uncertainties or sheer bad luck would somehow always prevent you from succeeding. The gun would jam, you would miss, someone would intervene, whatever it takes to preserve consistency. This seems contrived and raises the question of how nature knows what needs to happen to maintain consistency. It suggests a form of cosmic censorship that goes beyond the usual laws of physics. Asterisk, the many worlds interpretation of quantum mechanics offers another resolution. In this view, every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. If time travel is possible, traveling to the past would automatically create a new branch of the multiverse. You could kill your grandfather in the new timeline, but this wouldn't affect your original timeline where you were born. In a sense, you wouldn't be traveling backward in your own timeline, but rather sideways to a parallel universe that happens to be at an earlier stage of development. Asterisk, this resolves the paradox, but at the cost of accepting that an infinite number of parallel universes exist, most of which we can never observe or interact with. It also raises philosophical questions about personal identity. If you travel to what you think is your own past, but is actually a parallel universe, are you really time traveling in any meaningful sense? The people you meet there are not the same individuals from your own past, but rather parallel versions with different histories. Once you arrive, asterisk ## time travel in fiction and cultural imagination. Asterisk, long before physicists began seriously investigating the possibility of time travel, storytellers explored its philosophical and dramatic possibilities. H.G. Wells' novel The Time Machine, published in 1895, introduced many of the concepts that still dominate popular thinking about time travel. Wells imagined a mechanical device that could transport a person through time, just as a bicycle transports them through space. This mechanical conception of time travel has persisted in popular culture, even though modern physics suggests that any real-time machine would need to manipulate the fabric of space-time itself, rather than simply moving through a pre-existing dimension. Science fiction has explored virtually every possible variation of time travel scenarios. Some stories involve closed time-like loops where the time traveler's actions in the past are what caused the present they came from, creating a self-consistent loop with no beginning or end. The classic example is Robert Heinlein's story By His Bootstraps, where a man becomes his own ancestor through time travel, creating a paradox that somehow resolves itself into a stable configuration. Other stories explore the butterfly effect, where tiny changes in the past create massive alterations in the present. as in Ray Bradbury's A Sound of Thunder, where stepping on a prehistoric butterfly changes the outcome of a future presidential election. These fictional explorations serve an important purpose beyond mere entertainment. They allow us to think through the logical implications of time travel in ways that pure mathematical physics cannot easily address. They force us to confront questions about free will, determinism, personal identity, and moral responsibility that arise when we seriously consider the possibility of changing the past. If you could travel backward and prevent a terrible tragedy, would you be morally obligated to do so? What if your intervention might cause unforeseen consequences that are even worse? These are not just abstract philosophical puzzles, but questions that would have profound practical importance if time travel ever becomes possible. The psychology of time and memory. While physicists study the objective nature of time, as measured by clocks and the evolution of physical systems, psychologists and neuroscientists investigate how humans experience and perceive time subjectively. Our sense of time passing is remarkably flexible and context-dependent. Time seems to slow down during emergencies or novel experiences, and speed up during routine activities or as we age. A watch pot never boils, they say, because paying attention to the passage of time makes it seem slower, yet in retrospect, periods of our lives filled with routine seem to have passed in the blink of an eye, while periods filled with new experiences and memories seem to have lasted much longer. This psychological time is intimately connected with memory. The past exists for us primarily as memories, neural patterns in our brains that encode information about previous experiences. These memories are not like video recordings that capture events with perfect fidelity. Instead, they are reconstructed each time we remember, reassembled from fragments and filled in with details that may or may not be accurate. Our memories of the past are constantly being revised and updated based on new experiences and information. In a sense, the past is not fixed at all in our minds, but is constantly being recreated. This raises interesting questions about what it would mean to time travel. If we could travel backward to experience the past directly, would we find that it matches our memories? Or would we discover that our memories have distorted and transformed the past into something quite different from what actually occurred? And if we could somehow change the past, would our memories automatically update to reflect the new timeline? Or would we retain memories of the original timeline that no longer exists? These questions blur the line between physics and psychology, between objective and subjective reality. Some philosophers and physicists have suggested that consciousness itself may be intimately related to the arrow of time. Our subjective experience of time flowing from past to future, they argue, may be a consequence of how conscious minds process information and build models of reality. Perhaps the flow of time is not a feature of objective physical reality at all, but rather an artifact of how consciousness constructs its experiential world from the timeless equations of physics. If this is true, then time travel might not be about moving through an external dimension, but rather about altering the information states in conscious minds. Practical experiments and current research. Despite all the theoretical obstacles and paradoxes, some physicists continue to design and conduct experiments that probe the boundaries of what might be possible regarding time and causality. We have already mentioned John Cramer's retrocausality experiment, attempting to send quantum information backward in time by a few microseconds. While the results of such experiments have been ambiguous and controversial, they represent serious attempts to test whether the laws of quantum mechanics might permit some form of backwards in time influence. Other researchers are investigating whether the quantum vacuum, the lowest energy state of empty space, might contain enough exotic matter or energy to create the negative energy needed to stabilize a wormhole. Experiments with the Casimir effect, where two metal plates placed very close together in a vacuum experience a force pushing them together, have demonstrated that quantum effects can produce something like negative energy density in certain configurations. However, the amounts produced are incredibly tiny, far too small to have any macroscopic effects, let alone stabilize a traversable wormhole. Some physicists are also studying the properties of rotating black holes, also called Kerr black holes, which have even stranger properties than non-rotating black holes. The mathematics suggests that inside a rotating black hole, there might exist closed time-like curves passed through space-time that loop back on themselves, potentially allowing time travel. However, reaching these regions would require surviving passage through the black hole's event horizon and inner horizon, where tidal forces would almost certainly destroy any object made of ordinary matter. Even if someone could somehow survive these forces, there is no way to send information back out through the event horizon to the external universe. So any time travel would be trapped inside the black hole forever. Another avenue of research involves studying the very early universe, particularly the moment of the Big Bang itself. Some cosmological models suggest that our universe may have emerged from a previous collapsing universe, or that it may be cyclical, going through infinite cycles of expansion and contraction. In some of these models, information or even entire structures might be able to pass from one cycle to the next, creating a form of time travel across cosmic epochs. However, these ideas remain highly speculative and face numerous theoretical difficulties. *# the Fermi paradox in time travelers * one of the most puzzling questions in science. Is the Fermi paradox, if intelligent life is common in the universe, why have we seen no evidence of extraterrestrial civilizations? One possible answer that relates to our discussion of time travel is that advanced civilizations do exist, but they have not visited us because they have better ways to explore the universe than traveling through space. Perhaps they have learned to travel through time instead. If time travel becomes possible for sufficiently advanced civilizations, they might choose to explore their own planet's past rather than spending enormous resources traveling between stars. Why travel thousands of light years to visit an alien world when you could travel backward through time to explore the infinitely fascinating history of your own planet? An advanced civilization with time travel technology could observe every moment of their world's history, from the first emergence of life to the rise and fall of ancient civilizations. This would be far more interesting and relevant than visiting distant planets that might be barren rocks or at best host simple microbes. However, this explanation for the Fermi paradox faces some difficulties. If time travelers from advanced future civilizations are visiting the past, why don't we see evidence of them? Perhaps they are very good at hiding their presence to avoid contaminating the past. Or perhaps the time travel technology can only take them back to the moment when it was first invented, as we discussed earlier, meaning that all the tourists from the future will only start appearing after we finally build a working time machine. This would explain why we don't see them now, because they can't reach back further than the invention date, which apparently has not happened yet. Another possibility is that time travel is possible in principle, but turns out to be so phenomenally difficult and expensive that even advanced civilizations rarely use it. Just because something is theoretically possible doesn't mean it's practical or worth the effort. Perhaps time travel requires the energy output of an entire star, or the manipulation of exotic cosmic strings that are extraordinarily rare and difficult to work with. In that case, even civilizations millions of years more advanced than us might have achieved time travel in principle, but use it only rarely for the most important purposes. *#. Ethical implications of time travel. If time travel ever becomes possible, humanity would face ethical dilemmas unlike any we have confronted before. The most obvious question is whether we should attempt to change past events that we now view as tragedies. Should someone with a time machine travel back to prevent World War II, the Holocaust, or other great evils of history? The initial answer seems obvious. Of course, we should prevent such atrocities if we possibly can. But the matter becomes more complicated upon deeper reflection. Any significant change to the past would have cascading consequences that are impossible to predict fully. Preventing a historical tragedy might also prevent the births of countless people who were born after that event, including potentially the time traveler themselves. Is it ethical to sacrifice the existence of billions of people, even to prevent a great evil? And who gets to decide which historical events should be changed? Different cultures and individuals have vastly different views about what past events were tragedies, and which were necessary or even beneficial. There's also the question of historical responsibility. If we change the past, we are in some sense erasing the history that actually occurred, including all the people who lived through it and all the lessons that humanity learned from those experiences. The suffering of past generations would not merely be relieved, but would be erased from existence entirely, as if it never happened. This raises deep questions about the value and meaning of historical experience. Is it better to have suffered and learned from suffering, or to have never suffered at all because someone from the future changed the timeline. Asterisk, these ethical questions become even more complex if we consider the many worlds interpretation, where changing the past creates a new parallel timeline. In that case, you wouldn't actually be preventing a tragedy in your original timeline that would still have occurred. You would merely be creating a new timeline where it didn't happen. Meanwhile, the people in your original timeline would still have experienced the suffering. Have you actually accomplished anything morally significant? Or have you just created an additional universe that happens to be slightly better than the one you came from, while doing nothing to help the people in your original timeline? Asterisk hash has the ultimate limits of knowledge. Asterisk, our exploration of time travel brings us face to face with fundamental limits on human knowledge and understanding. We have made extraordinary progress in understanding the universe over the past few centuries, from Newton's laws of motion to Einstein's relativity to quantum mechanics and the standard model of particle physics. Yet for all this progress, we still don't understand what time really is at its most fundamental level. We don't know whether time travel is possible in principle. We don't know why time has an arrow. We don't even know if time truly exists as a fundamental feature of reality, or is merely an emergent phenomenon. Asterisk, this should inspire both humility and wonder. Humility, because it reminds us how much we still don't know, despite our impressive technological achievements. Wonder, because it suggests that reality is far stranger and more marvelous than we can currently imagine. The universe has already surprised us repeatedly with phenomena we never expected: black holes, quantum entanglement, dark energy, the Big Bang itself. What other surprises await us as we continue to probe deeper into the nature of reality? Asterisk, perhaps someday, generations far in the future will look back on our current debates about time travel with amusement, the way we look back on medieval debates about how many angels can dance on the head of a pin. They will wonder how we could have been so confused about something they understand so clearly. Or perhaps time travel will turn out to be impossible, not for practical reasons, but for deep theoretical reasons we don't yet understand. Perhaps the universe has fundamental laws that forbid closed time-like curves and backward causation, even under the most extreme conditions. Asterisk, either way, the quest to understand time continues. Every experiment that probes the nature of time at quantum scales, every observation of gravitational time dilation, every theoretical advance in quantum gravity, brings us closer to understanding this most mysterious dimension of reality. We may never build a practical time machine, but the journey of trying to understand whether such a thing is possible teaches us profound truths about the universe we inhabit. Asterisk hash conclusion, living in time. Asterisk, in the end, perhaps the most important lesson from our exploration of time travel is not about whether we can travel backward or forward through time, but about how we live in the present moment. We are all time travelers of a sort, moving inexorably forward through time at a rate of 1 second per second. We cannot return to the past to change our mistakes, and we cannot jump ahead to see how things turn out. All we have is this present moment, this eternal now that constantly slips away into memory even as we experience it. Asterisk, this fundamental limitation is not a curse, but a gift. It's precisely because we cannot undo the past that our choices matter. It's because we don't know the future that life remains full of possibility and surprise. The irreversibility of time gives weight and meaning to our actions. If we could constantly go back and revise our decisions, would any decision truly matter? Would life have any meaning if it were just an endlessly revisable draft, rather than a story we write once and for all? Asterisk, our inability to time travel forces us to live with the consequences of our choices, to learn from our mistakes without being able to erase them, to accept that some opportunities once lost are lost forever. This can be painful, but it's also what makes us human. It's what creates the urgency and poignancy of human existence. We have only one life to live, one timeline to experience, one chance to get things right, or at least as right as we can manage given our limitations. Asterisk, so while we may continue to dream about time travel, to explore its theoretical possibilities, and to probe the boundaries of what the laws of physics might permit, we must also remember to live fully in the time we actually have. The present moment is not a prison but a gift. The future is not yet written, and that uncertainty is what gives our lives meaning and our choices significance. We cannot change the past, but we can learn from it. We cannot control the future, but we can work toward making it better. And we can choose, right now, in this present moment, to live with intention, purpose, and care for ourselves and others. Asterisk time travel remains one of humanity's most enduring dreams, a symbol of our desire to transcend our limitations and reshape reality according to our wishes. But perhaps the real journey is not backward or forward through time, but deeper into understanding and appreciating the time we actually have. In the end, we are all travelers through time, companions on a one-way journey from birth to death. The question is not whether we can escape this journey, but how we choose to make it meaningful while it lasts. That is the real challenge of time travel, not building a machine that can transport us to different eras, but learning to live well in the only era we're given, right here, right now, in this precious and fleeting present moment that we call today.